today, at least people would say that they could see how molecular simulation is really working in reality. So yeah, if they read about it, if they are not really specialized in the field, they will be wondering how these simulations can be performed and so on. And yeah, my friend and business partner, Alan, is also co-author of the famous book, Quantum Computing and Chemistry for the Curious.
Oh, okay.
So it's, yeah, he's really also is present in the audience.
Yeah,
Okay.
thank you, Taha, for the nice introduction. Yeah, looking forward to being part of the discussion.
Yeah,
me too.
we thank you. Yeah, to be part of this. Okay, thank you.
You're welcome.
Mm-hmm.
People are welcoming you, Alan, in the chat. So that's really yeah, nice. And today also we'll be discussing at the end, yeah, the expected computational advantage using quantum computers for molecular simulations is very also important question. And yeah, it will be, we will arrive to this question naturally after explaining the computational complexity in molecular simulations in general, and how they can be really handled or expected to be handled on quantum computers, and how we think we can be creative enough to run such simulations in near or far future. But also there is other interesting projects that can be applied in a short term as an extension for quantum molecular dynamics and so on.
I think we can start.
Okay, and then I have a short introduction. So whenever people are thinking in, they will not, they can find the good materials. We'll start in a few minutes. So I'm gonna share my screen now.
I have just one question. Do you have this link for this book, or it is possible to share?
Right. Yeah.
Chat?
Yeah. Hey, Alan, would you share your book, the link for the book? It's actually a nice book. It's about quantum computing and quantum chemistry. And it's actually explaining very well how to perform quantum chemistry algorithms on a quantum computers, how to run several algorithms, but also have a sort of computational comparison between the quality of the algorithms. So perhaps, Alan, if you want to say 1 or 2 minutes about the book.
Oh, thank you, Taha. Well, it's the title is Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit code. So what can I say? If you are curious, then this book is for you, regardless of if you are a student or if you are already studying quantum chemistry and you want to know more about the applications what can be done with quantum computing, and in particular the Qiskit open source framework sponsored by IBM. Or conversely, if you are well versed with quantum computing and you want to know more about quantum chemistry, this is a book worth having a look and even better purchasing. And whoever purchases the book is entitled to get for free the set of complete Jupyter notebooks, so you can have the executable version of the book if you want. You can replay all the examples, and there are lots of them in the book, and you can change the experiments and enjoy. So it's an interesting experience, and we target our book together with my co-author, Dr. Keeper Sharkey. We target high schools and higher students. So it's part of I would say, quantum education mission. That's it. Thank you, Taha.
Yeah, thanks, Alan, for the introduction over the book. So I'm gonna,
Sorry, Alan, I had a quick question. Should I get the paperback or the digital Kindle edition?
I suggest you get the paperback.
Yeah,
because it's the formulas, the symbols are better, rendered in the paperback version. And again, with the paperback version, you can access the Jupyter notebooks, and then in the Jupyter notebook, you've got the LaTeX high quality the formulas, and so the paperback. Yeah.
Okay. All right. So I guess, are we gonna start? Or we're just gonna start now? Is this what's happening? Yeah, we're starting.
Yeah.
Okay.
Thanks, Alan, for introducing your great book to the audience. And I'm now gonna perhaps I will. I think it's fine like this.
I'll just start real quick. Hey everybody, thanks for coming to the meetup group. We have Taha today speaking on the topic. So I don't know if you guys looked at Taha's LinkedIn, but he's very impressive background. Did his bachelor's degree in Egypt, and then did his master's degree in France. And now he's doing his PhD in the Netherlands, where the university he goes to, they founded graphene, the element. Is that true? Yeah, graphene, right?
Yeah, I heard. I'm not sure, but perhaps you have a better, more accurate.
So, pretty impressive educational background, of course. And he's also the founder and developer at Molcat, which I'm assuming that you're doing this in conjunction to your PhD studies, which is very impressive, of course. So it looks like you've done your PhD for 5 years now. Are you expected to finish soon? It's a 6-year program, right?
Yeah, it's almost, it's average on 5 or 5.5, something like that. So in a few months, the thesis should be handled.
Right, yeah. So currently doing his thesis on efficient algorithms for quantum molecular dynamics. Sounds super great. And obviously that is the reason why he is in this discussion today. So obviously I'm not super technical, but I'll try to break it down. So there currently is a calculation, the coupled channel quantum scattering calculation, but it's very demanding and computationally hard. So therefore, I guess Taha or his team looked at other efficient methods. The CSA method is one he looked at, which is obviously, it shows that it's more efficient, but he looked at other stuff as well. So that's the discussion that he's going to have today. Obviously, I could have done it way better, but yeah, cool. So, ladies and gentlemen, it's Taha, and I guess he will take the stage.
Yeah, thanks a lot, Elyong, for your introduction. It's really nice of you to do such thing. And thanks for handing the floor to me. So I'm going to share my screen now, and I will start with introducing the title: Efficient Algorithms for Quantum Molecular Dynamics, computing rovibrational transition rates in molecular collisions. So the title reflects the work. It is a recent published paper about how to construct efficient computational methods and algorithms to perform quantum molecular dynamics simulations. So I'm Taha Salim. I'm a PhD candidate at the Theoretical and Computational Chemistry Group at the Institute for Molecules and Materials, Radboud University, Nijmegen. The PhD supervisors and also the co-authors of this paper are Professor Gerrit Groenenboom and Professor Ad van der Avert from the same group. And this is the link for our recent publication in the Journal of Chemical Physics. I'm gonna elaborate more about my background. So I'm doing now a PhD in theoretical and computational chemistry. My PhD thesis is about simulating molecular collisions to compute rovibrational collision rate. This PhD project is involving constructing efficient computational methods because such simulations are computationally expensive and very time demanding. And such efficient methods would enable performing these complicated computationally expensive simulations. The work also involves making codes for high performance computing and simulation codes to enable such simulations. My master's was in chemical physics, and I did work on femtosecond lasers. The thesis work was in control of quantum interference processes using femtosecond lasers. So basically designing and fine-tuning parameters for laser to control a chemical reaction by controlling electron motion that can guide nuclear motion and so on. The thesis work was done in University of Paris Sud, and the coursework was done in University of Burgundy. Courses, of course, covered photonics, femtosecond lasers, quantum information, Bose-Einstein condensate, and molecular physics, and some other courses. My bachelor was in theoretical physics, and I'm from high energy physics background, so I did heavy study in high energy physics, quantum field theory, general relativity. And before that, I completed 2 years in engineering study in signal processing and electronics and communication engineering. And I have a minor degree in business. So the thesis for my bachelor was about how to construct a symmetry methods to construct superpartner Hamiltonian. This method is about if you have a complicated Hamiltonian you cannot solve, there is a way to find a partner Hamiltonian where the potential is easy or the formalism is much simpler. And in that sense, we can compute the spectra of diatomic molecules or larger molecules using only the variational principle, which is really remarkable in this. And this has introduced me to the world of chemical physics and all of expected fascinating applications in different fields like sensing, quantum computing, and so on from this. And I started the journey from there to France and to the Netherlands. We see here on, I see, Raja raised his hand.
Yeah. Do you hear me?
Yeah, I hear you well.
Yeah. So we are going for the computation for these molecular systems, which are interactable actually by current HPC facilities mostly. But there is a way out of density functionals which can handle these problems in an easier way. Is that correct? Yeah.
It depends on the application. So DFT methods, of course, they are generally system-based. So in reality, there is no general way of generalizing DFT methods to all systems. And of course, you have to test each functional for each system. So you might have a functional that works for some systems very well, and some others not. So it depends on the system and so on. So, but if you start from first principles, using deploying full quantum mechanical calculations, you always get exact results that really reproduce the physics of the system.
Yeah, okay.
Yeah, I hope this answered your question. And if people wanted to know more about me, I'm based in the Netherlands, and I'm studying at Radboud University, and this is my LinkedIn profile. For the future, I have academic goals and entrepreneurial goals. And for academic goals, I hope to extend my master's and the PhD tools and experience and the knowledge to create useful applications in academia and industry, but also to help in accelerating the molecular and the chemical design by constructing efficient algorithms to run molecular simulations, also involving machine learning and AI methods. Efficient algorithms would enable running computationally challenging parts in simulations, also involving quantum computers, and hopefully perform hybrid classical and quantum architecture and algorithms, explore and solve more physical problems, and naturally, and of course, collaboration and projects in both academic institution and the companies. The other entrepreneurial goals we have now is a project Molkit in the university, powered by Mercator launch, and it's part of Radboud University in Nijmegen, where they give a lot of training for business and preparations. And now we have a very highly skilled enthusiasts among the team with different backgrounds and expertise. And of course, there is a strong scientific ecosystem at Radboud University, especially in theoretical and computational chemistry. And Molkit, it is algorithms and the software services for molecular simulations and the chemical design, using high-performance computing and quantum chemistry. And among the members, we have Alan Chancey. He has introduced himself now, and he's also the co-author of the book. And Hanan Ibrahim, and she is based doing her PhD in Finland. And we have more other three members from Radboud University who joined recently to work on different projects. And we wanted to use quantum chemistry and quantum dynamics theory tools and algorithms to solve challenging problems in academia and industry, but of course to collaborate on various use cases. And if you wanted to reach me regarding research or entrepreneurial work, just you can email me or just drop a message on LinkedIn. Now let's talk about the paper. So the PhD project's about handling computational complexity while keeping a good and enough accuracy. And molecular simulations or quantum simulations of molecular collisions in general involves very large molecular systems, and they are computationally expensive. And in principle, we know that any algorithm can be parallelized. There is no problem in that. However, the question is, does it pertain to the correct physics? So parallelization is good, computationally good, but it is not always keep the same physics. So when we make approximation, we have to make sure that it has been driven or derived correctly to reproduce and pertain the correct physics that we are looking for in the given molecular system. And we always have that question, are the results accurate enough for the intended application? Typical molecular collisions, in these typical molecular collisions, the size of the matrices proportional to the number of the channel bases, the number of equations that are being solved, and the computational time scales as the third power of the number of the channel bases. Of course, in some other cases, it might vary, or in other methods might vary from that, might be higher or lower. But this is in the method that I'm using for that project. It is about that. Numerical solutions involve running or solving the equations for about many hundreds of steps. The larger the bases, the larger, of course, the computational efficiency for our algorithm. Here we see a diagram, which I will explain shortly for our algorithm. We see here in the lower plane, the full exact calculations, in the higher plane, our algorithm. And we would imagine that for one energy only to simulate the collision for one energy, given a total angular momentum quantum number and the parity, which I will also explain later, but I'm giving example about how the algorithm is working.
Okay,
One
Taha,
job-
we have one question. What is
Yeah,
a
please.
basis? What is a basis?
Yeah,
in
so
your-
yeah, thanks for the question. So the basis, when we solve or expand a Hamiltonian, we have to solve it in a basis, and the basis could be molecular states, but also they could be the channel interaction equation. So each equation represent interaction over one quantum number. It's called one set of a basis in that space. I will explain this shortly, but this is just a short definition of what is meaning a basis. And someone can imagine the basis as if we have the Cartesian space, we have X, Y, and Z. So X, Y, and Z are the basis of the Cartesian space.
I have a question. In your interaction are kinds of on quantum mechanical level, or you can put quantum field theory level?
No,
in
it's
this approach?
No, it's a quantum. Of course, quantum field theory would give the second quantization. We are not in that depth of mathematical detail on the presentation, but mostly I will highlight the quantum mechanical approach in general.
Okay, and we have also a question from Raja Nisar. Okay.
Yeah. So when we are talking about the basis, we are discretizing the mesh here. So are we taking into account some discrete basis or continuous basis?
The basis by sort of the computational definition, they are discrete because you are expanding in a basis function. Of course, you can make them as large as you want, but at certain point you arrive to the maximum limit of your space. So the
model space definitely grows on with the basis number of bases.
So you can think about it as Taylor expansion. Taylor expansion is not continuous, but you expand it in a basis. Also, you have one term plus the second, the third, the fourth, and at certain point you say, oh, okay, this accuracy is enough for me after the 10th term, for example.
Okay, so model basis could be like harmonic oscillator states or something else.
Right. I will explain this shortly in the next few slides. I will explain this.
Yeah. Okay.
So I will explain the harmonic oscillator basis and so on. But thanks. It's a very good question.
Thanks.
Okay, I think we can continue.
So back again to the algorithm. So for one collision energy in that simulation, to give you an idea about the computational complexity, if you are given one quantum number of the total angular momentum and one parity, you have to do a simulation for several hundreds of jobs. And in each job, for one job only, if the exact calculation take about 6,650 seconds, our new algorithm would solve this in 2 seconds only, retaining enough accuracy for the intended application because it's relevant from one application to another. Such a comparison is already published in the paper. I will share all the links in the discussion. But I would just say that test is done on a single Intel Xeon Platinum processor, and also you can check the type of the processor on the internet. So now we come to the agenda. What I aim from here, and mainly I aim for everyone to see how molecular simulation is working in general, how we make approximations for the Hamiltonian, and to keep the physics or the information that we need in the system. And to discuss a bit of the computational complexity and the new approaches from quantum computers to solve and tackle this. So in part one, I aim to define quantum molecular dynamics and, of course, the scientific and the business applications, the motivation behind the projects. The famous James Webb Space Telescope was the main motivation behind my PhD project. The use of CO2 or carbon dioxide molecule as a quantum molecular sensor in interstellar media. And we will discuss here the CO2 molecular states in that regard. In part two, hopefully I will cover the Hamiltonian generally. So to have a good look over how the Hamiltonian looks like, how to express Hamiltonian on a computer, to store these numbers in a matrix on a computer. I'll discuss briefly the quantum chemistry method CCSDT, and then several approximation to the Hamiltonian, what terms we switch off in a Hamiltonian in order to make the computation more efficient. Then after a short break, I will back to discuss the computational complexity of quantum molecular dynamics simulations, the high performance computing capabilities, and what quantum computing can offer, the R&D process, and then we will end up with a discussion. So now we come to the first question. What is quantum molecular dynamics? And actually, people think of quantum chemistry as the field to simulate molecules, and this is not correct. Quantum chemistry, it is the quantum mechanical treatments of electrons. Molecular dynamics is a way of how you treat or use classical mechanical treatments of the nuclei using, of course, some kind of force fields. But the combination of both would give birth for quantum molecular dynamics. And in quantum molecular dynamics, it's a combination of both. We use quantum mechanical treatments of both electrons and nuclei at the same time. So it's a bit general from the two, and it uses in the backbone quantum chemistry to describe the interaction between molecules, and of course some Schrodinger equation and so on to describe the dynamics. Here we come into what kind of applications for quantum molecular dynamics. There are several applications. I'm highlighting a few of them here, like can contribute in quantum sensing, have application in telecommunications, space sensors, astrophysics, cybersecurity, electric batteries, and so on. Quantum computing, it give better design for quantum algorithms and the simulations. In molecular qubits, it helps in design molecular qubits and molecular assemblers. Of course, it gives the models to describe the collision of molecules and the molecular interactions. And quantum control to use helps in studying molecules that they are under control by certain electromagnetic fields or magnetic fields. Chemical reactions, of course, to study reaction dynamics. And here we come to the main motivation of the project, and we see the connection between quantum molecular dynamics and the James Webb Space Telescope. Of course, there is a famous quest to understand formation of planets and the origin of life, and the expectation that James Webb Space Telescope could help answering such attractive and mysterious questions. And the classical story says that planets are emerged out of interstellar clouds. They are very flat, called the protoplanetary disks. These disks came out of something fancy. So we have a very big, gigantic nebula, and those nebula collapse by the act of gravity. And during that collapse, by the act of pressure and the other conditions, they start to spin, and a protosun is like formed in the middle, and then that very flat pizza-shaped interstellar cloud, it's called a protoplanetary disk, and this is ends up at what we know now as solar systems. And James Webb Space Telescope is about to observe such interstellar clouds and give insights about them. If we zoom in over one of these interstellar clouds of these protoplanetary disks, we can find they have many regions, but the main feature is that most of them, or all of them, have a protosun in the middle. And of course, there is a lot of key molecules in such cloud, like carbon monoxide, acetylene, methane, carbon dioxide. And the main aim is that James Webb would help studying this. How James Webb does that? Of course, the James Webb Space Telescope, it is a multi-billion project. It has the most advanced sensors and the detectors on board for IR radiation. And whenever it receives a spectra, every element in interstellar media have a fingerprint, and molecular astronomers and molecular physicists can identify this. I'm introducing this introduction to show a use case for quantum molecular dynamics using CO2, basically. So how quantum mechanics really resolve or help in such use case. So we have this, we have a control over these molecules and atoms, and we have here on the left different pictures for the different types of protoplanetary disks. As we see, all of them looks like flat, and the typical spectrum that are simulated looks like this as on the right. And of course, we see here few peaks for carbon dioxide. So basically, such a spectra have a lot of information about the interstellar media and about the conditions in these interstellar media. And molecular astronomers, molecular physicists, and molecular astrophysicists, what they wanted to do is to decipher that spectra. So the spectra reports a lot of information about the chemistry in this interstellar media. There's a lot of hidden information about the local, for example, the local temperature, the molecular abundances, the percentage of, or the existence, the abundances of these species, and much more information. But for the sake of the discussion, the goal is to decipher the spectra and extract the useful information. So in that sense, we have carbon dioxide as a molecular quantum sensor. Now, before I introduce and we go to quantum mechanics, I wanted to show you what is CO2 as a molecule and the vibrational modes of CO2. So I'm gonna repeat here. So CO2 is a 3 atoms basically, and we have 2 oxygen and 1 carbon in the middle. And this is called asymmetric stretch. This is symmetric stretch, symmetric motion, and this is the bend. I will explain this in a later, but this is just an animation to show you how these atoms are moving. So CO2 as a molecular quantum sensor, it has 4 vibrational modes because it is a linear molecule. 2 of them are IR active, so they can really observe it in IR band. The others are not in IR, so they cannot be directly observed. And we see here the symmetric stretch. It means that the 2 oxygens move in the same direction. Either they contract or expand. We see here the bend mode, where the molecule really bends like water. And we have 2 degenerate modes, so it can bend in a plane or out of the plane. And these 2 motions happen simultaneously. And then we have the asymmetric stretch, which means that the carbon goes in one direction, the 2 oxygens vibrate in the other direction. We see here the frequency of them, but the main message or the take-home message from this slide is that Fermi resonance has been discovered in CO2 because of a strong coupling between symmetric stretch and the bend in the bend over tune. And that CO2 really give a lot of information about these interstellar media. So now, how to describe the quantum state of CO2? We need now to label the raw vibrational quantum state. So for that, we use 5 quantum numbers, and we use Dirac notation to label the state. So we put the quantum molecular state in a Dirac notation. It's a very compact notation. Dirac loves compact notations and the drawing and so on. He loves the geometry, so he wanted to express quantum mechanics in a very compact, elegant way, and this is why he used these compact notations. And for that, we squeeze the 5 quantum numbers between Dirac in the kit of Dirac notation. And this is the definition of these quantum numbers. So the first quantum number represents the vibrations, the excitation and vibration of the symmetric stretch that we have seen. The second quantum number, nu2, represents the bend mode, the vibrational energy in the bend. So if V equals 0, it means that it is a vibrational ground state. If V2 equals 1, it means it is the first excited state. LV, it is represents what is called the vibrational angular momentum. So when we have the bend happen in a plane or out of a plane, it's like we can visualize this classically as a rotation, but I'm not gonna highlight this. It is irrelevant for the discussion today. What is relevant is the meaning of the quantum numbers. We have nu3, it is for the asymmetric stretch, and J, it describes the rotational states. So for any combination of vibrations, the molecule also rotates. And this seems obvious, right? There is no nothing fancy about this. Couple of terms we have to know about before we see the most beautiful coming stuff. The first thing is the harmonic approximation, which Raja was asking about, that we take vibrations over the normal coordinates. What are the normal coordinates? Every normal coordinate, it means that one type of motion is happening. So one type of vibration is happening over that normal mode. So the normal mode is a linear combination of atomic displacements where atoms displace over for one specific vibration. And the normal mode, in each mode, atoms vibrates harmonically with the same frequency, but with different amplitudes. So some of them reach a bit higher amplitudes, the other are not. And of course, normal modes are orthogonal, like the Cartesian coordinates. So we have seen how to describe a molecular state. This is very, very crucial in all fields, in quantum computing, in solid state physics, in quantum field, in everything, to how to describe really a wave function and name the quantum numbers. And what we see here is that the definition again of normal modes, and this is the shape of the normal coordinates. So they are special coefficients, but this is what we need to know in this slide, and this is the normal mode. Now let's come to the famous question, how people would extract or use information from the spectra, and why there is a problem in doing so. So the main problem is, here it comes. So they receive the spectra from any molecules from these distant interstellar clouds can be induced by two main operations, either by the IR radiation from the protosun, or can be induced by collisions. So you receive a spectra, and of course there is no way to send a person to know, oh yeah, this comes from collisions, or this comes because there is a protosun in the middle shines IR light on IR radiation on the molecules, so molecules get excited and so on. So we have two main processes to describe here. We have collisional processes and radiative processes, and we would imagine.
Hey, Taha, we have question.
Yeah, please. Please. Yeah.
Yes.
Yeah. So will that V1 or Q1 take part in this particular scenario? Because you're saying for asymmetric, it is IR inactive.
Sorry, what do you say? You mean asymmetric or symmetric stretch?
For the symmetric case, that is IR inactive. So,
right.
Does quantum number V1 or Q1, do they really have a part here, or they are just silent spectators here?
No, so they play a role in the spectra because Fermi resonance is the one that Fermi discovered in CO2 basically. It means that there is coupling between the symmetric and the bend, and then the symmetric can be observed in indirect way via the bend mode. But we are not talking about this now. We are talking about how they model the spectra in general, and how the spectra is being received, and it can be induced, can be as a result of what?
Yeah, so you are taking the superposition of all the states so that Fermi resonance should be taken into account.
Right. If we take the full modes, this is actually the upcoming one of the upcoming papers. that we are putting fully Fermi resonance. So this paper is about the computational work is to save the computational time, reduce it. Otherwise, the computation will be impossible or will take a very long time, more than the lifetime of a postdoc and PhD. And in the other work is about how to really compute a chemical physics simulation, so to reproduce or simulate these collisions.
Yeah, thanks.
Yeah, thanks for your question. So is there any more questions? Because I have seen some other...
There was one.
There is a question. And the collisions are between which molecules?
This is a good question. So these key molecules like carbon dioxide, perhaps I missed it in the slide, carbon dioxide or acetylene or methane can collide. In principle, they can collide with themselves. And they can collide with the most dominant species like H2, or they can collide with helium atoms, for example. So collisions are allowed. They can collide among themselves. So the CO2 can collide with another CO2. There is no way to prevent that. CO2 can collide with methane. So they can collide with themselves, with each other. But also they can collide with the dominant molecules, like the most dominant molecule, like a hydrogen molecule.
Yes.
And they can collide with the helium atoms.
Yes. Do we have a way to distinguish between these possibilities?
Very nice question.
Or to incorporate this distinction in the calculations?
So the distinction comes from, of course, for each type of collision, there is certain characteristics for the spectra. And if we simulate it using full quantum mechanical calculations, we can reproduce the exact numbers that would indicate what type of collision happened. So actually, we reproduce the collision that happens in interstellar media.
So the spectra gives us complete information in a way that we can interpret it after we see the spectra or simulate the spectra.
Right. So they basically receive a spectra, but they wanted to reproduce the spectra in order to make sure that the model, and they have astrochemical models to solve. And in that model, they need the number that I will talk about in these slides for collisions. And these numbers, when they plug it, they have an idea about the molecular abundances, the excitations of such molecules. And there is more information they can extract using the numbers we provide.
That's great clarification. Thank you so much.
Yeah, thanks for your question. I see another question here about the proto-sun. The proto-sun is just only, the word proto is meaning that there is a small young sun. So our solar system emerged from a protoplanetary disk, very pizza-shaped, like a big cosmic pizza, really. And was in this pizza have a small topping, which is the sun. And with time, the sun is not young anymore. And we have the sun that we know now. So the proto-sun is just the young, it's like a new star basically in the disk. Perhaps there is also a more technical definition. It's not in my mind now, but this is how I can just project the meaning or the definition to you in a simplest case.
Yeah. So here you are also talking about stimulated emission. So that is a highly sophisticated sort of a thing that takes place in the laser action. But do we expect that metastable state there as well? And so, then how do we do the population inversion in such cases?
So I just need to explain the slide first. Otherwise, I will answer a question before explaining the slide. So if you allow me for a few minutes, I will answer that question.
Okay,
hopefully during his away.
Yeah, like honestly, Todd, just go back. I feel like we're just gonna hold off on the question for a bit. He hasn't explained the slide yet, so
no worries, no worries. It's just very nice to have questions along the way, so to remind what is missing. But this slide is very important to explain. Now what we see here in this slide, we see two energy level system. So it's a very simple case. We have the ground state basically and first excited state. So this is E higher and E lower. And the way to arrive from E0 to E high is that can happen by two main processes, either by collision or by radiative emission or excitation. And the first thing is that when a molecules collide with another molecule or another rare gas atom, for example, like carbon dioxide collide with helium, it might have excitation or de-excitations. This process, we describe it or we compute their characteristics and probabilities using what is called collision rate coefficients. The other process called the radiative process, and in that process, the escaped IR radiation might make radiative excitation. This is BLUs, where L indicate lower and U indicates upper. Or it can have a stimulated emission, so the molecule is forced to emit photons, or spontaneous emission. The coefficients that are described here to describe one of these processes, so to describe the collisional process, we compute what is called collision rate coefficients, and the radiative processes are computed by Einstein coefficients. And the name Einstein is historical for such coefficients. And basically, by knowing these numbers, these constants, astrophysical scientists can perform their simulations and really extract and simulate the received spectra. Here we come into the dilemma that we have. So Einstein rate coefficients, the one coming from the IR excitation, the excitation, are known mostly for small molecules. However, collision rate coefficients are not fully known and are not fully computed. And for that, we see here a model done by molecular physicists for CO2 spectra received by James Webb Space Telescope. And what we see here the ground state. So we see the same quantum numbers that we have seen before, the symmetric stretch, the bend, vibrational angular momentum, the asymmetric and the rotational quantum number. Of course, the rotation in this one, in this big ladder. And here we see the ground state for combination of four zeros. The first excited state in the symmetric stretch. So the others are zeros except the symmetric stretch. And here we see the asymmetric stretch. So we have one and the others are zeros. So you can match these numbers with these digits and with these quantum numbers. And then we can identify the states. And basically what astronomers need is that what's the rate coefficient? So they know Einstein coefficients, but they need the rates. Okay, so what's the collision rate for going from 2 in the bend, for example, to the ground state? Or to go from the symmetric stretch to the ground state, or to go from the asymmetric stretch to the ground state, and so on. And then providing such numbers is what helps like keep the model alive and interpreting the spectra. So the take-home message again in this is that Einstein rate coefficients are known mostly for these small molecules, but collision rate coefficients are not fully known for these key molecules. And the goal is to calculate accurate collision rates. So here we see what is the problem. So there is a problem with a use case. People need some numbers to put in their model because there is a multi-billion project is outside, of course, this atmosphere of Earth, and it is not a ground-based telescope. It is hanging out in a Lagrangian point a few million kilometers from Earth, observing the deep space. So it receives a spectra, hours are expensive, and spectra need to be interpreted and simulated. So here is a formalism of the problem. The James Webb Space Telescope is about to be launched. Of course, when I started my PhD, it was not launched yet. So it will detect the high resolution spectra of CO2. Can you simulate the collisions of CO2 with helium and hydrogen molecule? And we need these rovibrational transitions of CO2 during the collisions. Of course, yes, this can be done, and we can use quantum molecular dynamics to simulate the collisions and to compute the collision rates. And quantum molecular dynamics provides the most accurate calculations from the first principles. So that simulation is really simulated quantum mechanically, so using quantum mechanical equations. Okay, so I can take questions before I go to this point. Now I define the problem basically, and if someone has
actually, I had a quick question.
Yeah, please go ahead.
Yeah, so pretty much like the algorithm, like you're just pretty much using it to find the unknown coefficient, right? Which is the collision coefficient. It's pretty much what you're doing, right?
Right.
Yeah. Okay. Just want to make sure.
Yeah. But can you repeat again so I can because I missed just the sound for a second.
Yeah. And then just like a follow up on that, like, so is the coefficient like does the number like signify anything? Is that like a probability, or is that like something, or is that just like something like you just...
So it's a good question. So what we compute is that collision rates are computed from they are like Boltzmann averaging over what is called the cross sections, and the cross sections indicating the probabilities of transitions.
Okay,
so
true.
They are related to, for example, the efficiency of the process. So, for example, now we are going to study the vibrational relaxation from the first excited state in the symmetric to the ground state. And the computed number will indicate what is the efficiency of this process to happen. So is this really happening more quite frequent in nature, or it's happening on rare basis, and so on. So these, because vibrational excitations, they happen in a different way from rotations, and such numbers indicate the efficiency. Of course, when collision happen, the energy might dissipate also and be taken by the collided partner. So imagine CO2 collided with helium, and the helium might take part of the energy, so the molecule can excite, and the helium can take part of that energy and go away. So you need to know this efficiency. Okay, what is contribute to the spectra? What is really taken by other molecules? What sort of mechanism is happening there? Because the only way what you receive is only spectra, and that's it.
Right.
And for that, they need. But if you simulate it from quantum mechanics, you sort of can see in a very elegant way the frames, like a movie, of how this process is really happening. So yeah, when a helium comes with this energy, might happen, and we get this number, and then they get sort of a behavior, and they can match it or plug these numbers in their model and simulate.
Right. So once you have like the coefficient and the Einstein, are you able to simulate an entire, like, let's say, like multiple particles of CO2 and helium, and like that's how they're using it to see like how the protostars are creating these like planets and stuff? Like, I mean, suns.
Yeah, it's really a very nice question. So they combine Einstein coefficients and the collision rates. They put this in a model and solve what's called the master equation, and this equation gives them the molecular abundances. And if they have the abundances, they can. This is one of things they can know, the molecular abundances. And for such a thing, there is other models to derive the chemical evolution of such interstellar media. Because at the end, you get a molecules like DNA. DNA was not there in the early universe. So there is also a formation of that process happens in very long time scale.
Right. Which is like the efficiencies of the collisions and okay, true. Yeah.
Right. Yeah, this is really true.
Yeah, cool. There were some questions though.
So thanks really for this nice question, and it's really nice to have. And I think
So I was talking about that metastable state. Is it there, or is it just the transition from the excited state to lower state by some other molecule hitting it or some photon hitting it?
So I didn't understand just the first part, because you are talking about metastable state, right?
Yeah.
We don't have a quasi states here, just only it's typical molecular states. There is other ways to define metastable states. I will come into a similar case during when I show the results, but of course we just can say that there is certain time interval or time duration for the life of each state basically. But this is can be either relaxed naturally or be forced by radiation. So like you can have a stimulated emission or you can have a spontaneous emission and so on. And this is basically what describes what happens to the state. I hope that answers your question regarding that type of problem.
Yeah, okay. Yeah, fine. So how many molecules you are simulating at a time?
What do you mean? You mean in the one simulation?
Yeah.
Now we are in the simulations that I'm talking about is simulation of collisions of carbon dioxide with helium. So carbon dioxide with helium. So we're talking about two monomers, two parts are colliding, CO2 and helium. In principle, we can collide more, but then we will have very large computational bases. And of course, there is a lot of math involved. So, so at some point, if we include more and more, the computations might be infeasible to be done at all. So this is why we keep studying two colliding partners at a time, or if needed, we can go for three. But there is limitation for what you can go because of the computational complexity of the problem.
Yeah,
but
of course,
also the mathematical model and defining the state and so on.
Yeah, thanks.
Working with polyatomic systems is not a simple business like diatoms because there is a lot of symmetry operations, molecular points groups, a lot of features that I'm not talking about here, but you can find it on the internet. It's involves a lot of math work in a short.
I just got a quick question again. Sorry about disrupting.
No worries.
But like, okay, so because of the limitations of computing, like you're only able to simulate one helium, one CO2 colliding each other, but you're given that information to find the different coefficient values, right? So once you find that, you theoretically, if the computing power was there, you can simulate like multiple of them interacting at the same time, right?
This is a very good question. The physics it changes a bit when you have three body collisions. So because now if we have a relation between two, if we have a third party involved, it will change the anisotropy and the space defined for that interaction. So we need completely another simulation.
Right.
And of course, it depends on the accuracy. Some people might approximate, like make a molecule very far and the two are close, and then like pretend to have like a quasi-molecule here. But this is very like another cases. But in principle, when you have three interacting atoms, then you have, or three interacting molecules, you have a new potential energy surface and another reaction dynamics and collision dynamics, basically.
Right. True. Okay.
But it's very thanks for the question. So I see a question related to classical computer or quantum computing. We will come to this question in the third part of the discussion of the presentation, and then we will really discuss the quantum computational advantage that can be taken, or the challenges there for such simulations. So here back to the recipe for simulating CO2 with helium. And please, Eliong, if there is a need for break or so, you just can tell me or so on. I will just highlight this slide and you can let me know if there is a break or so.
No, I think yeah, you're good to go.
Okay, thanks. So now we see an example for rotational vibrational transitions of CO2 induced by the collisions with helium. So now this transition will happen due to the collision. And we see here the harmonic oscillator. This is over one mode over the symmetric stretch. And these two oxygen atoms make displacement in symmetric way for that mode. Here we see the ground state. Here we see the first excited state in the symmetric stretch. And of course, vibrational relaxation can happen in two main ways. For example, via couplings. So because there is couplings between the mode and other modes, and then energy can be dissipated, or can be happened within, for example, collision with collision partners like helium and having inelastic collisions. And in that sense, we have the two collided partners again, but one of them relaxed to the ground state. And what we see here, we have here the molecule in the first excited state, and then it will relax or de-excite to the ground state. The most accurate simulation to perform to simulate this is the quantum mechanical methods, and the most accurate quantum mechanical methods are coupled channels methods. And of course, the coupled channels is just only solving the time-independent Schrodinger equation, and I will be highlighting this in a minute. I have a question.
Yeah, I have a quick question. So, like, what is the so the more efficient like it is, the more likely the atoms go from like ground to excited state. That's what it is, right? And also, what is the significance of an atom being in an excited state?
So this is just one example of many that could happen. For example, in this paper, we are taking a molecule that in the first excited state and relax it to the ground state. And of course, we can compute the reverse process from the microscopic reversibility, but this is another thing. And basically, if we have the molecule here and it goes to the ground state, that is described by a cross section, and the cross section will give an idea about the efficiency of this process. Of course, there is we can compute it where we say the molecule is in another state, will go to the ground state, or it is in the ground state, will go to the excited state, and so on. So you have all these combinations, but for each time we have to make one simulation, because such simulations also depend on the initial state that the molecule is already in. So if we have one run for CO2 when it was in the first excited state, this will not give us numbers for other states. It's only will give us number for this state going and relaxing to all these Vj. So it can give us the number to J prime here and there, but within the ground state only.
Right.
If we need different state, it means that we do another simulation, because one of the input parameters to the equation is the initial energy of the state, and the total energy is depending on it is the sum of the state plus the collision energy. So the molecule comes, finds for example, the helium comes.
Yeah.
I can just highlight this here in a second, if you just bear with me for 1 second.
I can give you one.
Yeah, honestly, Tom, if you want to keep going as well.
The atoms are like electrons and other quantum systems, that they don't like be in a higher state. So they probably take this from higher state. You will get lower state by some excitation of some photons. So we can check it, what kind of photons you get, and you can see that atom must be on some higher level or some low level. Yes, so this is first. And I have also a question, but maybe Taha will give you.
Yeah, my bad. I sidetracked this conversation. Yeah, you could just keep going, Tom, honestly. Or
yeah, you can just. I will answer your question and then ask Sebastian. After his nice comment about this. So just to not forget, so we have we can have a CO2, for example, in one state. So it can be here, and this is like initial state. And this we call it, for example, EV1, and then a helium atom would come with a collision energy, for example, EC, and then the E total is basically EC plus EV1, the initial state. So this is why this is a parameter that we should insert. So for each initial state, if the molecule is in, for example, V1, we have to do a run. If the molecule is in V2, we have to do another run, and so on. So it's not really everything in one, all in one. No, it is not the case.
Right.
So can
yeah,
I
please go.
give
So,
you-
yeah,
yes, so I have just one question. That in your picture, your states are CO2 molecules, yes?
right.
And you describe it by some quantum numbers, but in true picture, how you compare it to the electron and helium interaction? Because it's not CO2 interact with helium, but electrons and its components with other components of helium. Can you compare these kinds of interaction with this picture?
So in this picture, the helium is not there yet. We are. I'm explaining the CO2 levels, how can be relaxed. But of course, what you say is true. It will come in the second slide when the potential is introduced. So the quantum chemistry will play a role here, where we have to provide a potential energy surface that describes the interaction between CO2 and the helium. And this is basically the electronic contribution to the dynamics.
Hey, but at the quantum mechanical level, you just change the potential of Hamiltonian. But you say about collision and about kinds of inelastic and elastic interaction, and this is more connected with quantum field theory picture. It is correct to mix these two?
So the quantum, overlap here can be seen in a way that we can use a second quantization to express the Hamiltonian, which and meaning that we can make the Hamiltonian as E dagger A.
Okay, sorry, you can take second quantization, but your state are not elementary particle, but molecules, yes?
Right,
and you want,
yes.
You want second quantization take for molecules, not for elementary electron and protons and etc.
It is not. It's only now we because of course, as a harmonic oscillator to happen, it has to be like some bound states should be there, and the bound state comes from. Of course, they are bonded, so there is bond involved in like sticking the molecule together, the atoms to form a molecule, and in that we have these states. But the molecule is in the ground state of the electronic ground state, so there is no electronic excitations are involved. And of course, because the electrons in ground states can have Coulombic interactions, including dispersion and so on with others. Like, for example, when CO2 collides with another CO2, there is a Coulombic interaction, and this interaction with all terms, we describe it as a potential energy surface, and it is a one term in the Hamiltonian. It will appear in 1 or 2 minutes, this part.
Yeah, but you know that CO2 as a molecule has also it is also states of quantum mechanical, but it's huge approximation of true states of these kinds of molecule. Yes, because you assume that each electron is the same. You assume that you have something in the center of it, and etc. etc. So as I understand, at your level, at your beginning level, you treat the full molecule as a simple basic states of everything you do. Okay.
Right. Harmonic oscillator.
Okay,
right.
Okay. Thanks.
Because now we are doing one mode. This is thanks for your question because it's very nice point. What we do is now we treat it in this paper one mode at a time. So because the aim is computationally, if we add more coupling, if we add more modes, it means that we have higher, of course, we don't have one-dimensional oscillator, but we have 2D or 3D, or it depends on the involved states. And they will not really look like this for that. But for simplicity and to focus only on the computational advantage, now the molecule is restricted to this kind of possibility that you might find CO2 excited in the symmetric stretch and will go to the ground state. And then that can be visualized by when we are near the equilibrium by a harmonic oscillator behavior. And of course, these are the bound states. We have vibrational state and rotational states, and the molecule is in the ground, in the electronic ground state, so there is no electronic excitation. If we have electronic excitation, we will have two extra quantum numbers depending on the symmetry and the parity and so on next to these.
Yeah, okay, just to next quantum number, but the space of states will be huger, and
right,
it will be more complicated than just this simple picture.
Right. And the second thing is that electronic interaction in these are contributing very negligibly to this type of collisions. So there is no really, it is a very closed shell molecule. So if you have an open shell like OH, or for example, some other open shell molecules, then we really have to deal with electrons because they sort of have different symmetries and can contribute to the collision. But in this case, we don't have that because CO2 is a closed shell. So this is why the main dominant states in the electronic ground state is vibration and rotations. This is also why CO2 is very hard to be experiment with in the lab, because there is no, it is very hard to control it. There is no way to use the Zeeman decelerator or any other of mechanisms to control or guide the molecule, not like other open shell molecules. So the only lab that is really good to study CO2 is in space. And this is why they are looking for these kind of systems.
Sorry, Todd, you have 50 minutes left. So somebody asked a question, but you got 50 minutes. Yeah.
So so now what we see here is that require an open shell model. Yes, if we have an open shell molecule, there is way to manipulate it with external fields for sure. This is what I can say for now. Just this is very close, is a closed shell molecule, so we are not really interested in that at the moment. So so now what we see here is that we need to construct a good Hamiltonian to describe the system, and to do this we need to write a Hamiltonian for that mode to obtain the rotational vibrational wave functions and energy eigenvalues. And for that, we have three terms in this Hamiltonian. So the Hamiltonian here describes the system, and the way that we diagonalize the Hamiltonian, we can obtain the states, and the states will be represented by the wave functions, and the eigenvalues will represent the spectra or the energy of these states. And we have three terms here. The first term represents the nuclear motion. The second term represents the angular momentum, the rotation of CO2. The third term represents the 1D potential. Why it is 1D? Because we are only involving one vibrational mode over the normal coordinate. So here is the potential that describes the electronic contribution to that Hamiltonian. And that Hamiltonian can be need to be solved in these computational bases that we have seen. Now, all other quantum numbers are zeros except the symmetric stretch and the rotation. And this is how these wave functions look like. I'm not going to talk about it, but basically they involve spherical harmonics in it to describe the rotation. So if we have this good Hamiltonian, now we can go to the second step. And the second step about to have a bigger Hamiltonian to describe CO2 and the helium. And here comes Sebastian's question and also remark. we have the Hamiltonian here, and that Hamiltonian should describe the kinetic energy of the dimer. The dimer is referring to two involved parties, helium and CO2. We have the Hamiltonian of CO2 itself as a monomer, an isolated monomer. And then we have angular kinetic energy. So the complex by itself, CO2 and the helium, they also rotate around one another, and they have they couple to one another. So there is a sort of overall rotation. And this is expressed by that term. It's called angular kinetic energy of the dimer. And then we have a potential energy surface to describe the interaction between the helium and CO2. So they approach one another, as we see here. And the interaction is potential is described by that term. So we see here the helium, we see CO2, and we see here the bound state. When helium comes, CO2 will make a transition, and the Hamiltonian basically describes the entire system. Why I'm mentioning the Hamiltonian explicitly? Because when we do quantum, when we go to quantum computing or we do approximations, people often miss what kind of terms are switched off. So now it is a way to see which term we can switch off or we keep in the Hamiltonian. So this is the Hamiltonian is exact, and these are the all terms. And if we solve that Hamiltonian, it means that at the end we can obtain the collision rates. So our approach is that we compute the CC matrix as a solution, the matrix representation of to solve the Hamiltonian. Then make a numerical propagation to solve it, and then obtain the results in a space fixed frame. We have two frames here. I will not talk about any mathematical details in them, but we just I can just elaborate that in the body fixed is a frame that is attached to the collided parties. The lab frame or the space fixed is that when you see the system from above, basically you are in the lab. You are not on board with the molecules. And so I see here the question about the Q. So the Q is the normal coordinate represents, this is a nice remark. It is a normal coordinate that represents the symmetric stretch. So we were discussing together that every normal vibration or vibration happens over a normal mode, and atoms, when they move in this normal mode, they move on a normal coordinate, which is the combination of this atomic displacement. And this is basically a coefficient that represents how they displace in such that they oscillate with the same frequency and with different amplitudes. So hopefully this answers your question, Anurag, if I pronounce the name correctly. So now we come again to that. We do it in body fixed frame, and the body fixed frame, because computations are efficient, we can do approximations and decoupling schemes and so on. But at the end, we obtain the results in space fixed for physical reasons and so on, but it is irrelevant to our discussion at the moment. We wanted to talk about the computational advantage. And here we're back again to the Hamiltonian. And just for people who are curious, this is how these bases looks like. I'm not going to explain them, but they just look like this. So this is why having more collided parties is not really as simple as people would think, because there is a lot of math have to be worked out behind this, and this is involving a lot of complicated coupling and schemes. And again, we solve this Hamiltonian. We can solve it in space fixed or body fixed, but we choose the body fixed frame. At this point, I'm now highlighted the Hamiltonian. So if you wanted to take a break for 5 minutes or so, I'm fine with it. If people really feel dizzy or too much information or so on.
Actually, you can stay until the very end. I'm always staying for 3 hours. Don't worry about timing. We all will be on time, but hopefully I see a comment from Joe. Thanks for your comment. It's really appreciated, and thanks Helen for expanding the time for me. I just hope that yeah, as Sebastian was discussing, to not really inflate the time a bit.
I think that everyone will wait for your information about quantum computing and simulating these kinds of because maybe yes, there is a lot of people who try to do something with quantum computation, and this is hard problem, and I think that this will be very, very important and very, very nice to see, and we will wait.
Yeah. Okay. Yeah. Thanks, Sebastian, really for your comment. At the end, I'm showing the problem now to see why it's there is a challenges to perform this on a quantum computer, but to see it in reality or to highlight this, I don't want to burn as a surprise. But we have to wait as you said. So okay, now we come to how to represent that matrix on a computer. This is very, very important point, because here is a computational prospect and perspective for that equation. So we have an equation. We solve this equation in a basis. So that basis gives the space that or like Hilbert-like space that we solve that Hamiltonian in. And that space is composed of the basis or the all allowed states that in that system. And we have the monomer states of CO2, but also we have what's called the channel bases. And it means that when helium collides with CO2, there is also another channel basis coming from the total, from the angular momentum part. And then the overall basis, we solve the Hamiltonian projected in that basis, and then we get a matrix representation. The matrix representation with all of these numbers in it, this is actually what we solve at the end. So there is two main important matrices in this Hamiltonian. Of course, CO2 Hamiltonian, we get the rovibrational wave functions. This is a representation of it and the energy eigenvalues, and this has become a sort of constant of column of constants. The first important matrix is what is called the angular kinetic energy, and this one represents a term, and V represented the potential or the interaction potential. Two main remarks in the body fixed frame. We have here omega, and we have here omega, and I see a question here that about the quantum number in the bases. I can just highlight them quickly. So V here is the vibration, J is the rotation, omega is the simultaneous projection of the rotation of CO2, the Z projection of CO2 and the total angular momentum on the Z axis. So the simultaneous, it's like a simultaneous eigenvalue. I'm gonna define it shortly, but this is how it looks like. J and the MJ, this is a total angular momentum quantum number, and the MJ is a projection of it in a space fixed frame. Here we see L, and the L is the orbital quantum number in the space fixed frame. So this is basically the quantum number. I'm gonna highlight them again, but hopefully this is briefly answers your question. So we have the matrix representation. At what we see here is that the potential is diagonal in omega. Omega is the simultaneous projection, as I have said, of the total angular momentum and the CO2 angular momentum on the Z-axis in the body fixed frame. And being diagonal in omega, it means that we can use omega to parallelize the solution because it is diagonal. Why it is allowed? Because if we have diagonal matrix, it means that every block has no information or it is not connected to the other, so it can be taken alone and be done separately. I can just highlight this point here. So it can be taken separately, and this is very crucial in that sense. So if we have a block diagonal like this, it means that if it is diagonal, we can do the computation separately.
If you're doing something, we can't see it on the screen.
You can't see on the screen. Okay, I see. So
all we see is your slide. If you're drawing something, we don't see what you're drawing.
this is a good that you told me about this. I will just.
So everything you've been talking about, see this matrix? You see these? We haven't seen any of those.
Okay, I'm gonna fix this issue at the moment. It's good that you told me because yeah, Zoom sometimes behaves quantum mechanically, so it's very surprising sometimes. Okay, now you see this. Because now Zoom allows for sharing
okay.
one of the content. Yep. Okay, so now we see this is if we have a block diagonal matrix, it means that every block is independent of the others. So omega 0, omega 1, omega m, they don't know anything about the rest because off diagonal blocks are zeros. So everyone can be taken away, and we can do the computation over each one separately. So omega, if it's the potential is diagonal in omega, it means that there is a good way to parallelize the computation, and omega is a good quantum number. So I will highlight this in the slides. So this is written in the slides, but this is just to give a head in advance about this. So I'm back again to the slide. Now we see the second term. It is block diagonal in omega, but also there is off diagonal omega blocks. So every omega is coupled to omega plus 1 and omega minus 1. So one term is diagonal in omega, the other is not. And then this term represents two terms in the Hamiltonian. It's very important to see this, so that U matrix is acts like 2 in the Hamiltonian, the potential acts like 1, and we have already discussed the rest. Now I've spoke explicitly about the monomers Hamiltonian, but I didn't speak about the potential itself, how we compute the potential, and here is the quantum chemistry part in the simulation. Quantum chemistry part, it means that we have to compute a 3D interaction potential energy surface for the dimer. Why it is 3D? Because it involves 3 coordinates. Q, which represents the normal mode, the vibration of CO2, R, which represents the distance from the helium to the center of mass of CO2, and theta is the polar angle between R and the z-axis. So CO2 is placed on the z-axis, and theta represents that projection, basically. So when theta is 0, it means that the helium is on the z-axis. The potential is computed using what is called CCSDT level of theory. This is a gold standard of computational chemistry, and the abbreviation is for coupled cluster with single and double and perturbative triple excitations. And this is used to describe the interaction potential. And if we need to do so, we have to choose basis set. And the basis set is that we use this type of basis set augmented by some functions. This is also details, but the take home message here is that we have 3D interaction potential. We have to compute that potential over a grid for each coordinates in Q, R, and theta. And then we have to fit the potential. And the fitting is really important, because this is how you reproduce your AP initio computed points. And the fit has to be good. Otherwise, you might really miss a lot of useful information in the interaction if the fit is not really reproducing the configuration or the part of the space that you are really interested in, or does not really reproduce the anisotropy or the directional dependency in the interaction. Because CO2, there is like tiny variations in anisotropy. It means that the energy dependence on directions with respect to helium. The reverse way for anisotropy is isotropic. It means that the space is identical, is almost homogeneous. If we have isotropy, it means that it's like a fixed interaction, but the anisotropy, it introduces variations in the directions. So the fit has to be good, and then we have to expand the potential. It means that we obtain certain coefficients in order to compute that matrix. and I'm not gonna highlight this detail, but the main point here is that this potential is computed over quadrature points. Now here is the fun. We come to see the matrix on a computer, how it looks like. And this is how the matrix actually looks like on a computer for two energy levels. So we see here two quantum numbers. We have the nu 0, which is vibrational ground state over the symmetric stretch. We have V1, which is the first excited state. So we have the rows and the columns, and the rows and the columns because of the bra and the kit that we have seen. So we have the kit is in the columns, the bra comes from here, and this is how the matrix look like in that basis or that space. If someone has questions at this stage, you can answer before we go into deeper into that.
Yeah, why Jacobi coordinates?
This is a good question. So Jacobi coordinates, they are good for this type of fit and expansions. But of course, because we're also using the spherical representation of Schrodinger equation, but some other people might use different types of coordinates, like hyperspherical coordinates or others, and involves another representation. So, but for that, because this is convenient for this system that we are dealing with.
So in that sense, can I make my life theoretically easier if I found another set of clever coordinates?
Yes, like
Not that I have them.
Like in classical mechanics, you can find that sun is around Earth or the other direction. So yes, if you choose good coordinate system, your life will be easier.
So
yeah, thank you, Sebastian.
Consider
That's true.
that. People consider it because we are talking efficiency here. So that may mean you tell me that you talk about efficient computations, and I believe you and respect it, but there is always room to do better in that direction.
So the basis is different from the coordinates. So the coordinates here is basically to is used to for the potential to be computed and describe the Schrodinger equation. So now we see in Schrodinger equation, now we see the R, that is this R that's used in the potential. And of course, that R is also in the kinetic energy, but this is could be treated as the simplest way of seeing exact computation like this. Some other people, because they have reactive scattering, they use hyperspherical coordinates, and it's a bit more complicated. So the coordinate by themselves are not the big issue. Of course, they are big issue, and theoretically, as you said, they can be theoretically challenging to drive the correct terms and the correct formulas. But the computational complexity comes from the number of bases or channels, because for each equation, there is a set of quantum numbers that have to be solved, and then irrelevant of how this Hamiltonian is described in the space. After all, we have quantum numbers that the equation have to be solved with respect to. And here it comes the computational complexity.
But if I can comment, this is a classical problem, because if you have two-body problem, you can reduce to the center mass. So you change coordinates and you get solution, like
Right.
for one body problem. And you can say that, but if you take three bodies, you cannot find such a good coordinate. So as you see, this is the same like in the helium atom in ordinary quantum mechanics. So you reduce two body to the one in the center of mass.
Right, and this is why now we are, according to what Sebastian said, now this is why we see here the mu, and this is the reduced mass of the complex. And this is actually done in the center of mass of CO2 and the helium. I just didn't tell that theoretical detail because it might not be It might be over complicated to part of the audience, but yeah, as you said, is basically this one is really represented in the center of mass, and then we get this reduced mass, and this is the reduced form of the Hamiltonian with respect to this.
The question could be, sorry, the question could be how exactly we get approximation from CO2 and from helium, because this is important, because not so good approximation from these two states could give you different kinds of results.
This is very good question, and this is what will come into the result. So actually, people in the literature have worked out a lot of approximations, like to assume certain physical assumptions, and make the simulation based on. And based on that, they decide how the reaction or the dynamics will go. So actually, there is approximation can be done for each term that can reduce the number of bases. We have seen in the previous one of the previous slides that, for example, a very simple job might really easily involve 6,000 channels, and we talk about 6,000 by 6,000 as a matrix, and this is the simplest case. If we have many modes, it can really easily scale to 50,000 by 50,000 and even 100,000 by 100,000. And then at certain point, the RAM more than 2,000 gigabytes or 3,000 gigabytes will be needed to perform such computation. So after all, in this simplest case, people have worked out things to shrink down the bases, but on the expense of the quality of the results. And this is also another issue we have to take into account. So I see George saying that he still sees a block diagonal omega matrix on the screen. Is this the case for everyone, or everyone is seeing Schrodinger equation?
I think we see the equation.
Oh, okay, so
Yeah.
perhaps yeah, here's a zoom.
Yeah, you gotta keep going. Yeah, just keep going. Just go. Go.
Okay, so now we have seen that we have like 4 blocks now. We have blocks now defined by the vibrations, and we have 2 vibrational states only. And we have another blocks labeled by omega, and the omega is the eigenvalue of both GZ, JZ, and of the CO2, and big JZ of the entire diameter of helium CO2. So we have the total angular momentum and the angular momentum of CO2. So this one rotates in a total, and also CO2, the GZ component of them, the simultaneous projection on the Z-axis, is called the omega. So actually, omega can be used to sort the matrix, because now we see omega 1, omega 0, omega 1, omega m, and so on. And of course, because omega is connected or computed from the rotation of CO2 and the total angular momentum, for each vibrational block, there are a bunch of omegas, and there are off-diagonal omegas. So these are the diagonal blocks of omega that we see here. We see a block diagonal. It means that every omega is like a little matrix in it. Little matrix, and so on. And we see here off-diagonal blocks, and these are blocks that are really off-diagonal. So it means that if we have these off-diagonal blocks, we are no longer can use omega as a good quantum number to parallelize the computations, because omega 0 have some information to know about omega 1, because there is one like little nice off-diagonal block here that communicate the information between them. And this is basically the CC formalism in that body fixed frame. Now we come here to the computational complexity, and the simulation is distributed over separate jobs. For each collision energy, each job performs a CC calculation, the one that we say is a time-independent Schrodinger equation in spherical representation. And we see here for each total angular momentum, we have parity P, and if we have 2 vibrational blocks, if we have this bunch of rotational states, and for each little j and the big J, we have blocks of omega. And if we need to converge, there's a lot of total angular momentum quantum numbers are involved. And it means that for each job, we are solving at minimum or in average 6,000 equations. So we have to solve 6,000 equations for 150 jobs. And we are talking about one mode with 2 states. I mean, imagine if we include up to V equal 4, then how this is with the scale. So this is, here we see the computational complexity. Now we know about it in molecular simulation, quantum molecular simulation, because classical have a different ones. I see here a comment 2456 is for a basis. Okay, I probably, yeah, we'll discuss this in the discussion afterwards. So we have the computational time scales as n to the power 3. And n is the number of the channel bases. So the channel bases means the number of equations. And then if the number of equation, for example, is 6,000, make it cube, then you get an idea about how the computational time should look like. If we have more modes, it means each one has its own rotational manifold, rotational space, more angular bases, and then computations really might take months to be completed on a medium-sized cluster. So this is really the computational complexity. People in 70s couldn't do such accurate computations, and 80s. And for that, there is a lot of invented decoupling schemes or approximations. And the solution to use such approximations or decoupling schemes should be done under the following conditions, should satisfy providing the required level of accuracy, the needed accuracy, for example, for the type of experiments that are being done and the precision and the accuracy that's involved in the design, but also to keep the general physical properties untempered, so unmanipulated or changed. So that slide, the take-home message in it is the computational complexity and why it is really, those questions of are really important of involving many bodies. Like if we have 2 molecules, 3 molecules, 4 molecules, and everyone has its own molecular bases, and we have this angular momentum and the channel bases to interact with one another. Imagine the size of these matrices, how it would look like. And this is why going to DFT and so on, but of course it depends on the level of accuracy that is needed. So here we come to Sebastian's question about what approximation could be done for such equation. And actually the first one from the literature, it is called vibrational close coupling infinite order sudden. And for that, we see that the full CC matrix is reduced to 2x2 matrix for the 2 vibrational block. Why is that? Because basically they assume that the molecular rotational time is much more smaller than the collision time. So if you have a CO2, the time that CO2 takes to rotate is very small comparing to the time that the collision is happening. And in that sense, when helium comes every time, it will find CO2 just in one direction. So it might find it in this angle, in that angle, in that angle, and so on. And this is really crucial here because it means that we can do the dynamics over fixed orientations. And in that sense, we don't really need all of these off-diagonal elements. And here, what we switch off the term in the Hamiltonian. And this one is approximated. And then all of these nice omega blocks are gone, and we end up having a 2x2 matrix. It's literally 2x2 matrix, like really 2x2 matrix, very trivial matrix. So what do you expect as an accuracy for such approximation? And now we have, this is accuracy. And what we see here from the accuracy is that we see here 2 computations. Yeah, I'm not fast. I was explaining what term should be switched off. I will slow down in this a bit. Thanks, Ken. So what we see here is that we see 2 curves. The red one is the vibrational close coupling, infinite order sudden approximation, the VCC IOS. And the black one is the coupled channels approximation, or coupled channel, exact calculation. And we see on the x-axis the collision energy, the relative collision energy, the relative energy that the molecules approach one another with, and the integral cross sections, the one that we compute the collision rates from. And then what we see here, thanks, Helen. And what we see here is a very big difference between the two lines. So you see the exact calculation, and the VCC IOS is really, really way below for this vibrational relaxation. So if the molecule relaxed, the efficiency of this process or the collision rates is really out by few order of magnitudes. Okay, that's really lovely and nice. So should we use it or not? So this is what we see. We see the computation's quality is really bad. Few order of magnitudes of difference. Nowadays with these high resolution machines, is not really acceptable even in 70s or something. So let's go to see the timing. So the exact calculations, if it takes 3 weeks, for example, to compute one grid, the IOS can be done in 2 to 3 hours. So you can go to have your lunch and then a bit of coffee, chat with colleagues about some fancy event or anything, or have some jokes, and then the computations are done. But on the expense that the quality is not that great, actually. Not actually that great, it's just very bad because there is 2 or more order of magnitudes difference between the actual result and the approximated one using the VCC IOS. One more information I need to say about that graph is that we see here these like fancy structure, and this is called resonances. And resonances, I had one question from the audience was talking about the meta states. And I think Raja or perhaps another colleague, and the resonances here, they indicate the lifetime of the complex. And basically because we get a width in energy, because this collision energy, this is energy scale. From Heisenberg relation, we have a relation between the width in energy and the width in time. And this one's approximated to h bar or h bar over 2, but like around h bar, like a constant from Planck's constant. So if the delta E is very small, it means that the delta T is very high. And hence, when helium comes to CO2, it doesn't leave the system. It means that at this range of energies, they will stick together for some time and form a quasi-molecule, a quasi-complex. So that complex will have a certain lifetime, and that lifetime can be computed and indicated using Heisenberg relation. This is just one side remark. Okay, so now we see that the VCC IOS is not that great. So there is other approximation where people really worked hard to get it done, and it is called the coupled states approximation. And in coupled states, all of diagonal blocks of omega are switched off in the Hamiltonian, and we ignore the Coriolis couplings in the angular kinetic energy. And what this means in the equation, basically in terms of mathematics, it means that we throw away all of these off-diagonal nice little omegas. All of them are gone, switch them off. We remember that we have seen 2 terms for the angular kinetic energy. One of them now is gone. And this will give us a nice result that we will have only omegas alone. And if omegas are alone, there is the off-diagonal blocks are zeros. It means that there is no information dependent whatsoever between the nearest neighboring omegas. So the omega 0 wouldn't know any information about omega 1, and omega 1 wouldn't know about anything about omega 2, and so on and so forth. And for that, we can do we can parallelize the computation using omega. Omega is a good number, and the computation can be parallelized. This is the game. And now let's see that and how it looks like. So we have we can do the computation for each omega. So we can solve the matrix for omega 0 alone independently, because now it's parallelized. That big matrix can be now separated into small components, and with a computational time advantage, the one that takes, for example, a day can be done in half an hour or so, and so on, because now we have to shrink down this. Then we do this and this and this. So we have omega 1, omega m, and this is how we do the propagation. And then at the end, we propagate each omega alone, and in that approximation, then only the monomer states of CO2 are coupled, because there is no coupling. CO2 now doesn't know anything about the Coriolis coupling of the entire complex. There is no relation, no information. And this is the quality of the results. I will zoom in on one on the figure, and this is what we see. So we see different CSCA with different curves. This is just a different representation for the diagonal elements. It's out of our scope, but we see that 3 of them are really, when the energy goes high, they deviate very badly from the exact results, which is in black. So switching off that in the Hamiltonian resulted in these bad. This is why we are talking about what type of accuracy we need. The approximation should be done within a physics perspective, and so on. And then we see that deviation here. One curve is very flying away. The other is having a 4 order of magnitudes or so. This is another figure, shows that they sometimes become close, but the other one is deviating, and they keep oscillating in that pattern. Overall, we have a factor of 3 to 5 difference. And now let's look into the timing. The timing is that if coupled channels take about 3 weeks, coupled states, all of them will take about 2 to 3 days. This is just the normalized numbers to give you idea about how the time behaves for entire grid of computations. So it is not bad if we need accuracy within a factor of 3 to 5. But the question is it accurate enough for the astrophysical model? And this is the question. Yeah, it looks like no, because now James Webb has a nice detectors on board, and the nice IR cameras, and a very fancy instrument in space, basically. So it deserves better results, right? We have a fancy machine, so it needs really fancy numbers, basically. And this is, here it comes, our approximation. This is combined with another method. And this is the last computational slide that I'm gonna showing now. And in that approximation, we use what is called distorted wave-borne approximation, used with enhanced version of coupled states. The enhanced version is called coupled states plus the nearest neighboring coupling blocks. Why it's called that name? Because in the propagation now, omega is propagated with the off-diagonal omegas. So it's propagated with the previous one and the next one and the off-diagonal ones. So we have like 9 by 9 matrix to propagate. In CSA, we have 1 block only, but now we have 3 by 3 blocks. So we have 9 blocks to propagate. Sorry, 9 blocks, not 9 by 9. So it's 3 by 3, 9 blocks. So I have 3 by 3 block matrix to propagate in V0. And if we have the same bases here, rotational bases, we have the same 3 by 3. And overall, we propagate 6 by 6 blocks. So it is still a bit expensive than CSA, but it is cheaper than the exact results. And here we see what is the distorted wave-borne approximation. It is an approximation in which the vibrational couplings are treated using the perturbation theory. And that one is really different from the Born-Oppenheimer approximation. So it is another work. So Born had a lot of works to do, and one of them was using the vibrational couplings. And if we combine this with the enhanced version of CSCA, we can treat the rotational couplings using this trick of propagating every omega with the nearest omegas, nearest blocks, and make the vibrational couplings using the perturbation. So this means that colored blocks can be taken away and computed separately, and then we end up having 2 blocks for each vibration, and then we can propagate each block independently. So it's like we divide the saving in omegas to 2. And this actually turned out to be pretty useful and very gives a pretty decent result. Here we see in the independent results for the NNCC. NNCC basic is a theoretical formalism of NNCC was published by Yang in a Chinese group first, and we have combined with the NNCC the distorted wave-borne approximation to get that nice efficient algorithm. And we see here that the results when we go away from the resonance part go match with the exact results. I'm gonna highlight this here. Yeah, please go ahead.
Yeah, sorry, Tom, quick question. So I'm just trying to interpret the graph here. So like the fluctuations in the beginning is like the actual collision occurring between the 2 molecules, and then like it's just balancing out at the end, right? Like there's just like an end state between the 2 interaction, right?
Yeah, this is a very nice question. So in the beginning, what we see, what we see here, I was just do you see my screen? Because I don't see my screen.
Yeah, it's like the distorted wave-borne approximation. It's like the zoomed-in graph.
Okay. So thanks that you are seeing it. So now in that approximation, what we see in these resonances is that at that time, molecules take more time to interact. So there are a lot of quantum mechanical behaviors are going on. And for that, we see these sharp resonances. And the resonances means that molecules, because from this Heisenberg relation, that they stick together for some time, but also they move slowly when they approach one another. So they have time to interact and talk to one another, basically. And for that, we see these resonances structure. It means that there is some states that can resonate with one another, and also a different energy exchange of energy mechanisms that could happen.
Right.
And this is different when we go to higher collisions. Certain parts of the potential is not playing any role at all, and it's like the short range interaction is happening. So molecules really hitting one another, so they have anisotropy around the vicinity of the molecule, and this is how it is done basically. So the first one is related about the resonances. It's the way that the complex is forming like quasi-bound states. So helium stick with CO2 to spend some time together.
Some wild stuff going on, yeah.
Right, there is a lot of stuff, and also a lot of quantum mechanical behavior, like certain wave expansion and interactions that happen, and also things that might happen there, but this is roughly the basic idea.
Okay, true. So like at the end, so I don't want to take your time, but at the end there, so like when you see like the curve at the end, that's like the what happens at the end of the interaction, right? That's like the coefficient of.
So now this is a good question. So I perhaps explain this quickly. So what we see on the x-axis is different energy. So it's different collision energy. So for example, the CO2 can collide with helium at one wave number. Wave number here is a translation to the Kelvin. So the Kelvin here is translated to wave number. So wave number and the Kelvin, one of them is 1.4 from the other. And that means that the energies that they approach one another with.
Oh, right.
So they might approach one another with one wave number, which is here. And that one means that we can have cross-section about 2 10 to the power minus 3 angstrom square, for example. And if they have 10, then we are around 10 to the power minus 4. And we see here that the resonances are very high. And once we go down, nothing happens. It's like basically nothing happens. And then we start to have growing again. Why is that? Because at the resonances, the molecules have time to interact, and then the excitation process will happen more efficiently. and then the cross sections will be very high. So this is why you see probabilities really cross section are really big here. And then after some energy, the vibrations are not affected anymore. So the collisions is not really affecting on the relaxation process. But then helium, when with more and more energy, when we go to 1000, it hits the molecule and then force the molecule to de-excite. So now we see if we go higher and higher, we get classical mechanics on board, because now we have really very high energy. So the time taken for quantum mechanical effects to happen is no longer there, because it's really very fast collision. But when we are in a slow motion, like they are sensing one another via very far interactions, and they approach one another and very slowly. It's
very slowly.
Very slowly.
True.
This is just for the sake of the time. I'm not giving all of these
details.
Yeah. But
yeah,
it's very good question, by the way.
Going back to the slide though, so like in this couple state nearest neighboring coupling, this one here. Sorry, the slide that you're just at. Yeah, it looks like it's pretty accurate in the classical, but like in obviously that it's still inaccurate in the lower part of the graph. Sorry.
Right.
Continue. Yeah.
And then you see that this coupled states, the ones that we propagate with omega blocks only, you see how it deviates from the NNCC. So now you have sort of very good matching here. But this one is huge, and for that, because there is information to exchange between CO2 rotation and the complex angular momentum motion. So they have really coupling; they interact with one another, so they are correlated, and that information are encoded in the off-diagonal blocks. So the off-diagonal of omega, they have this information how they talk to one another, basically. Now here we see the combination of both the distorted wave and the enhanced version of CSA. And what we see here is on the x-axis, we see the final rotational states. And then we see here on the y-axis the cross-sections. So I hope, Eliong, that your battery is not dead.
Yeah, sorry, I had to just move to a different room, but yeah, sorry.
No worries. No worries. Yeah, it happens all the time about this battery.
Yeah.
So you have the here two axes, and the y-axis is just about the final rotational states, and the x-axis about the final rotational states, and the y-axis about the cross sections. And we see here the cross section at every final state. So we see here initial state J equals 0 and V equal 1, going to different final states at different energies. And here we see a different final state, different initial state, going to all of these final states at two different energies. And we see that the distorted wave with NNCC can reproduce these results, and it's almost identical. So the distorted wave combined with NNCC can really make a substantial saving for the computations. Thanks, Cynthia. It's really late to have afternoon, night on Saturday for that. And now we see here the computational advantage that we get, that using this approximation, the distorted wave with the enhanced version of coupled states can really make a substantial saving in time. So the exact calculations, if it takes about 6,650 seconds, the new algorithm would do it in 2 seconds. And we have like 1,560 as a division between both in saving. It means that we have less computational time and less memory. And this test is, of course, was done on for one job only. Those comparisons were done on a single Intel Xeon Platinum processor from that generation. So now let's go to the computational complexity and achieving the quantum computing. Before I go to this, I need to, if there is questions related to the previous part.
I guess not. I guess just keep going.
Okay.
Yeah.
So now we have seen the computational complexity of that and of these quantum molecular simulations and dynamic simulation in general. We have seen that there is several approximations are tested, and they took a lot of time to be tested and make sure that reproduce the correct physics. These approximations are used to make a parallelization for the simulation. So they are really used for that. The CC method as a time-independent method is very time-demanding and requires a lot of time and the computational resources to be performed. So now, what we observe next to the computational complexity for that problem, we see one thing: we have to have predefined matrix elements. We have to have predefined the information to plug into these simulations. Right? We had the CO2 molecular states to put in the Hamiltonian. We had the potential to put in the Hamiltonian. We had a lot of information to include in the Hamiltonian, and this is all predefined. And the main goal was to have the main goal of quantum molecular dynamics is to have accurate, fast, but also better chemical and molecular simulations. How we can have better simulations with this computational complexity? If we need to have exact computation, very accurate, very precise, it means that we really need a lot of computational resources for that. And these computational resources is used for the CC method, but next to that, the CC method also require a lot of memory because there is a lot of predefined information that have to be plugged in the Hamiltonian before running the simulation. So the question here comes: can we perform such computations fully on quantum computers? This is the first question. And if someone wanted to tell an opinion about this before discussing the answers, then it will be a good point to get into interaction mode.
I don't think so.
Okay. So thanks, Alan, for replying. So now we see here that to achieve the computational advantage, there is a lot of challenges to do so, and the main one of them is the quantum memory. The CC simulation or time-independent methods, this one are really accurate in space fixed or body fixed, but they require predefined information, and this predefined information should be stored somewhere. So one of the main issues is to solve or to overcome that challenge is to get away or have a method that does not really require a lot of memory. The second thing is the number of qubits, because now we have a lot of and a huge number of the configuration on the Hilbert space. We have all of these bases. The number of qubits plays a role to perform such computation or to enable them, and also the fidelity. So now we see that in molecular physics, it is not about quantum computing only. It is about the way that you frame or derive your Hamiltonian. So actually, it is very safe to say that 90% of the work depends on the good formalism of the Hamiltonian. This also was taught many times during the last summer school of IBM, of Qiskit, about the amount of work required to derive and formulate a Hamiltonian. So the good Hamiltonian can really be mapped easily onto a quantum algorithm if it is really derived in a smart way. So we are talking now about how to, what is needed in quantum molecular dynamics to really run such a simulation, or what is required for a quantum molecular simulation to be performed on a quantum computer. So we can say that the first thing, we need to overcome the challenge of the quantum memory and have a Hamiltonian that really don't require much of information predefined. The second thing, we need to have a Hamiltonian that can be mapped in a good way to the spin Hamiltonian. And these, or of course, for each type of architecture, there is several ways to formalism, but this is the simplest case. We have a sort of transformation to be done to map that Hamiltonian from the classical formalism into a suitable quantum formalism. So how we can do that? We have a sort of multiple ideas to proceed and conceptual designs for such algorithms that we will start with as an extension work for the PhD, either on academic level, but also in the Molket project. And the first thing, it's about to use quantum Fourier transform combined with time-dependent methods. Now we have seen that the time-independent methods, the ones that is not really dependent on time, they are really exact. They really depend on what you put. If you have a good potential, then you have a good result, basically. But the time-dependent method require to have optimization for the initial state and does not require much of a predefined information for the simulation. So now we come into the first challenge, that we can overcome the first challenge by combining the use of quantum Fourier transform with the time-dependent methods. The second thing is the formalism of the Hamiltonian. So the Hamiltonian has to be in a time-dependent format, and it has to be formulated using a smart way to be mapped directly on a quantum algorithm without too much wiring or lengthy circuits. The third thing is that also there is ways to, we have an idea how to make a hybrid classical quantum approach, and in that sense, we can construct efficient algorithms for computationally expensive parts. We see that the most expensive part is the solution itself of this Euler-like equation, which is Schrodinger equation. And that part, the heaviest part, is the solution. And of course, if there is a clever way, and we have an idea how to do so using the combination of what I have said before, then we can overcome that part, and then we use the predefined matrices in classical or high-performance computers and do this expensive computation in quantum computing hardware. Of course, this would require some R&D work, because to develop a good formalism of the Hamiltonian, you have to make these tests that we have seen, but the results are rewarding, because once we have a nice way to formulate the Hamiltonian, it can be generalized in certain coordinates, and it can be used for small molecules, and hopefully it can be generalized. And this is basically a plan to how to overcome that challenge. So we have several challenges to overcome, and all of them require funding, but also require certain use cases to work on, experiments that are running, and sort of business that is going on in order to compare and model such systems. And for that, we aim by constructing classical quantum approach is a way to perform the dynamics. So dynamics is really important, because it is not only about James Webb Space Telescope. It can be used in drug discovery and simulating protein folding. There is many ways to expand the space of the applications of quantum molecular dynamics. One last thing to say in this discussion, I think it's too late, and I won't really go into more depth about other mathematical formalism, but I wanted to say one crucial comment, is that defining or searching in quantum algorithms have also another advantage, because it helps to explore more physics in the system, so to explore more properties about the systems. So now we have seen in coupled channels, we wanted to compute accurate collision rates. If we have a better formalism, and we have from Etamar, if I pronounce your name correctly, is asked a very nice question about to have clever ways of formalizing the coordinates and so on. And defining nice Hamiltonians, it means that we can see, we can span more physical properties and see more characteristics in the system and handle more applications. And in that slide, I can take more questions or any available question before we go to the second one. Let's see. I will see. Yeah, thanks. Thanks, Mariam. Yeah, so here in that presentation, we are not really answering a question of Abdel Ali Farragi. And here in that presentation, because of the time, of the sake of the time, there is no, the elaboration on the quantum algorithm is very short. Perhaps it is for another presentation to be done. But the take-home message here was to show the complexity, the computational complexity of performing such a computation. So now the quantum hardware is still lacking the memory. So the memory is a big issue, because we have seen that we need to predefine in certain methods. We need to have a really huge predefined information. However, using another clever approach, we can just try to get rid of that and have a better definition for the Hamiltonian, not a better in a sense of a physics, but it's better to be mapped on a quantum hardware and be efficient. And once we have a paper or have a product over that, I will be happily be here to share those.
Someone has their hand up.
Yeah. Yeah, please go ahead.
You're muted.
Hello.
Hi.
I have one question. This total simulation is started from time independent calculations. So here in the quantum algorithms, you are saying time dependent methods we need to use. But how the problem become time independent from the starting, and how one need to see the time dependency?
Thanks for your question. If I understand it correctly, you are asking about how the methods, the time-dependent methods, are compared to time-independent methods, right? Hi, Sereno. If I this was your question. Did I understand it correctly like that?
Yes, partly. And my question is, we have this collision problem, how it become time independent starting, or if somebody wants to see the time dependency in the Hamiltonian, how it will be incorporated.
So thanks for your question. So if we now we start from the time independent method, because it's like having an idea that we visualize the full collision from scratch. So we say that the collision will happen from that distance to that distance, and we compute an interaction potential. So it is this is why it's predefined interaction potential. So we have a certain distance with a certain length, and for that we have a predefined factors, and we solve the time independent Schrodinger equation. This is pretty exact results. It can reproduce many experiments. There is a lot of groups, and including our groups, using that method, they can match with the experiments with many digits and so on. So the method by itself is exact because everything is under control. The potential, and if the potential, as much as the potential describes the interaction much better, as it goes better and better, the quality of the cross sections becomes better and better, and so on. So the collision simulation is becoming much better and better, but the algorithm itself is very accurate, it's very exact, and represents the systems. So time-dependent methods use different approach, and sometimes it's computationally efficient, but it has to be played with some smartness, because now you assume certain states that will be propagated, and along the way you are updating that states. So having a predefined in the ones that we use in the time-independent methods, there is a lot of information under control and a lot of terms under control, and things are under control. And time-dependent is a different approach. How they are compared to one another, it depends on, of course, on the system. Ideally, Schrodinger equation, they are equivalent. The time-dependent part is equivalent to the time-independent part. However, for that system, we didn't try it yet because we were more about having one good exact result and a nice computational efficient algorithm that can perform, enable such computation and perform it using a well-defined algorithm from the literature, which is called the coupled channels method.
Okay, thank you very much.
Yeah, I hope this answers your question. Otherwise, yeah, we can talk more about, I can refer to you to other papers. I'm trying in the answer to avoid a bit of mathematical complexity, but you can chat with me on LinkedIn and I can refer to you to the sources that you need to see how they behave comparing to one another.
Thank you.
Yeah, thanks for your question.
There's two more questions, but it's 3:20. So did you want to just finish it and then I'll just remember these questions to ask you in the end?
Yeah, sure. So now the last slide is about the research work. So from after that, there's also a couple of more papers coming on the way regarding the question of Fermi resonance. The bend mode is a bit, my life got stuck with CO2 for some time, but it was fun to play with CO2. It has a lot of fancy mathematics and some surprises. So there is a way to collaborate on the research work. I'm open for academic and industrial collaboration, and we are open as in MolKit project for potential use cases, collaborations from academia and industry. And if you wanted to contact me, you just can drop me an email on these two emails, or you can just chat with me on LinkedIn and I will reply to you very shortly. Any general inquiries are really welcomed. So any question, any idea, anything you have in mind, just drop it out. I will be happy to chat. It's very pleasant to chat about these methods. There is also a lot of unknowns that need to be known, of course. And together, I believe we can do everything and we can achieve certain decent computational algorithms, but also a very good hybrid way to enable performing computationally challenging simulations. So I see a question here, why is the time independent is a valid approximation? Yeah, so thanks for the question, Ken. So it is valid approximation because it's, of course, there is also many ways to answer that question, but if you are talking about the validity from a computational perspective, it is an exact method based on the time-independent Schrodinger equation and represented in this type of coordinates. And for that, if we define each term and solve each term in that Hilbert-like space, we can get a matrix representation for the Hamiltonian, and for that we can simulate the collision and obtain the necessary information that is required either to understand the collision, to understand this mechanism of collision, but also for potential users of these simulations. Yeah, thanks, Angie, for your presence. Really, thanks a lot. I hope this answered you, Ken, for that. There is also other methods people are using, but this is the one that the group was using for longer times and they have expertise in, matched with experiments with very high number of digits. It's a lot of success coming from that method.
Sorry, there's one more question. Oh,
yeah,
sorry.
Please go ahead.
Can I know something more about this? What is this MolKit project?
So MolKit project, so now as part of the entrepreneurial goals, it's a bit of fancy word. The MolKit project, I got training from a part of the university, and it's a project under the university in a stealth mode for a potential academic startup, and that still under the umbrella of the university. It's not abroad yet. Alan is a part of the team and a very active collaborator. Hi, Alan, again. Yes, late evening. So, and in Molkit, we aim to leverage the expertise and the tools that we have now, many tools in the computational algorithms and designing them and handling them on high performance computers. And we aim to leverage this type of knowledge into formulate the good Hamiltonians for quantum computers, but also to use this knowledge for other use cases and other problems, like designing quantum sensors. We are working now on a conceptual design for a quantum sensors that can be used in network for cyber security. It can be used for ultra cold gases sensors also as well. So we aim to make algorithms and software tools for simulations, but also to provide conceptual designs for certain small machinery systems that can help solving different problems in academia or industry. Also to explore more phenomena and more system on academic level, like to learn more about collisions, simulate more certain type of collisions and molecular interactions and so on. And this is basically Molkit. And if you want to collaborate, really feel free to drop me a message on LinkedIn or the Molkit page, and we'll be happy to connect with you and see what kind of work we can collaborate on.
Yeah, there's one last question, I think. So somebody asked, any thoughts on bandwidth / latency requirements with the quantum computer in a hybrid system?
Yeah, Shaheen Khan. Yeah, thanks, Shaheen, for this nice question. It's a bit of a difficult question. This is really a very tough one because now there is many algorithms. A few of them, of course, suffer, not few of them, like many of them suffer from the bottleneck connections between quantum classical hardware. There is a recent paper that was published about 10 algorithms that can be done on a quantum computer for beginners. I forgot the name of the authors, but I will be happy to drop it to you in the chat if you contact me on LinkedIn. And in that sense, they were also complaining about the computational bottleneck of classical quantum hardware. Are they solved? There is also a lot of clever ways to solve it. I'm not familiar with all of them, but yeah, it also will be part of the challenge that has to be overcome along the way.
I just had a question about your entrepreneurial venture. So Molkit right now, are you mainly based on partnerships or are you generating revenue right now? Like, do you have a customer that you're working with or?
Yeah, it's a really nice question. So it is still a project under the umbrella of the university. We are welcoming any partnerships, collaborations, academic research, industrial use cases, and so on. So it's still starting a project. We are a team of highly enthusiastic people. Like the whole team is highly skilled with different expertise and different backgrounds, and they are looking forward to present some nice conceptual designs, but also nice solutions, algorithms, and so on. So this is still a baby, like a baby, like organization, I would say, under the university. The university is supporting such activities, and in order to learn and grow, and we need to extend academic and industrial collaboration. So also, if you wanted some collaboration, feel free to drop it any time. And if other one of the audience wanted to collaborate with us, is really welcome to do so.
May I ask some questions?
Yeah, please go ahead.
Okay. First of all, is the situation about CO2 in the lab was unique? So you had to look at space only. And then the other question is,
so just can I know what do you mean by unique?
Unique, namely, there is no other situation that we cannot deal with in the lab. We had to go to space.
So you mean just to because this is very important question. So you mean that why we go to space and not use CO2 in the lab?
No, I accepted your statement that you had to go to space and you cannot deal with it in the lab.
Right. Yeah, just to paraphrase the statement a bit, just about that CO2 is being studied by James Webb in that interstellar media. But next to this information, CO2 cannot be easily controlled in the lab. So this is why it's very hard to do such experiment, like experimental work on Earth, basically.
So maybe if there are other situations like that, maybe we can learn from the experience about CO2 in the space, so we can deal with this a posteriori in the lab. And so that's especially after the the experience, after the success of your calculations, maybe then we can draw a conclusion for the future in CO2 or other situations which are similar. Maybe then we can alleviate the difficulty that was in the lab and apply it.
Yeah, so if I understand your question correctly, and please correct me if I didn't do so. So the CO2 by itself is very hard to do experiment with in the lab. So people use, of course, supersonic beams and so on to compute such vibrational relaxation. But because it is a closed shell molecule, it is very hard to control and study the collision dynamics of it. So the only way is to do a theoretical model. Because also those molecular astronomers and the molecular physicists, they have a lot of collaboration with experimental groups, and they could ask them easily to perform such an experiment. However, the problem is that they cannot do such thing because CO2 is very hard to control and so on, because it's a closed shell. It also has no dipole moment. I mean, except of course for certain vibrations there is a dipole moment, but it's very hard to control, not like open shell systems. So the only way is to do that on a computation and observe it in space, because in space it can collide with helium. Also on Earth, in atmosphere, there is also a lot of people who do similar situations, or we can do similar situation by tweaking our model a bit and include it in the atmosphere of Earth or exoplanets and so on, and provide such computations. But in the lab, they don't really have an idea, too much influence on CO2, because in order to do so, you really need to have very hard control machine. And this is basically the quantum sensing. If you have open shell molecule like NO, for example, you can use certain fields to control it and select the state of that the molecule is in, and then make a collision after. Hopefully this answers your question. If not, yeah, we can discuss it again.
Yeah, well, it's 3:30, we're already half an hour over. I think that's the last question that we're probably going to take, unless someone had like a question they want to ask. But yeah, once again, Todd, thank you for the presentation. Thank you for letting us know the difficulties.
Yeah, really thanks a lot. I just wanted to mention the acknowledge, and then yeah, thanks for you for organizing such a nice event, Sebastian and Helen, and you, Eliong, and then my PhD supervisors, Professor Gerrit Groenenboom and Professor Ad van der Avord, and the theoretical and computational chemistry group at our university, and the MolKit team, including Alan Chancey and Hanan Ibrahim, Mercator Launch, and of course the funding agency for the PhD, and the one that gives really the money to do such research. And this is a university, and the funding agency was done to network like a branch from the NWO. And this is, yeah, my last slide.
Sweet. Yeah. Thanks for the shout out. I will make sure to follow Molcat on LinkedIn, just to follow and see how you guys do in the next couple of years. But yeah, best of luck with PhD, of course. And thanks for coming by and presenting on the topic today.
Yeah, thanks Eliong for that, and really thanks for everyone for the presence. I hope it is not really too much of a lengthy presentation.
Cool. I think that wraps it up, Helen. Do we just close now? Like, I guess we're done.
Sure, you can close out.
Okay. Well, thank you, everybody. Just log out, I guess. Unless you guys want, yeah. Cool. Cheers.
Thank you.